relative age dating. How old is one rock or feature in a rock compared to another? How old is the bottom rock compared to the rock on the top? Well, the bottom rock is older, but now we're going to move into the next topic where we can be a little more specific and absolute age dating. So we're actually going to figure out what is the age. How old is that rock layer? So not just talking about relative compared to another rock layer, but specifically how old is a rock layer. And before we get into that, we need to remind ourselves of a friend of ours, the periodic table of the elements. Remember, there's 92 natural elements, a few man-made ones, and everything that is a thing is made up of these right here. I really want to focus our attention on carbon. So notice where carbon is on the chart right there. Carbon is made up of a bunch of protons, neutrons, and electrons. All of them are made up of protons, neutrons, and electrons. The electrons are the ones that zip around the outside. We've got the protons and the Jimmy neutrons are on the inside, or the nucleus of the atom. Carbon, you'll notice on the periodic table, carbon says it's 12.011. And what that is, it's the mass or the number of protons and neutrons inside the nucleus. So if we take a look at two types of carbon, so here is a carbon, and this carbon has 6 protons and 6 neutrons. So we call this carbon 12. And when we go back up and take a look at our carbon, notice that carbon says it's really 12.011. Well, the vast majority of carbon is carbon 12. But every once in a while, we get some carbon that has 6 protons, but it's got 8 neutrons in there, and that's carbon 14. Carbon 12 is 99%, over 99% of all carbon is carbon 12. But every once in a while, we get this carbon 14, and we say that this carbon 14 is radioactive. The reason that we say that's radioactive is the nucleus of carbon doesn't want to have 14 in the nucleus. It wants to get rid of some. So occasionally that's what happens, is one of the particles will leave and eject out of the nucleus, and when that happens, energy is given off. This is radiation. So when a particle is radioactive, when an atom is radioactive, we say that it gives off radiation when one of the particles leaves the nucleus. So carbon 14 is radioactive, where carbon 12 we say is stable. Carbon 14 is unstable. So some elements change and become a different element. And the example that we used is that carbon 14 is radioactive, it is unstable, and it will change. It will stop being carbon 14 and it will become something else. This is common. Radioactivity is not something that only happens in the movies and turns Bruce Banner into Hulk. There's a lot of different things that are radioactive, even the things that you eat that are radioactive. So some of this radioactivity is not necessarily harmful to you. On page 1, the front page of the Earth Science reference tables, there's a list of 4 radioactive materials. Now, there's a lot more than 4, but there's 4 that we're going to use in Earth Science to help us find the absolute age of rock layers. There's our friend carbon 14 that we already spent some time with, but the others, potassium 40, uranium 238, and rubidium 87, those are radioactive materials, and we call them radioactive isotopes. So just understand that when we use the term isotope, we're talking about one of those 4. What do they turn into is given under the column of disintegration. So carbon 14 we say is radioactive and it changes into something else. It changes into nitrogen 14. Potassium 40 changes into argon and calcium 40, where uranium 238 turns into lead 206, rubidium 87 turns into strontium 87. And then there's the half-life, which is how long this process takes. More on that later. Understand, though, that when we look at this, for instance, the uranium 238 and its disintegration, it says it goes from uranium 238 to lead 206. It's a little bit more complicated than that. Uranium-238 actually then turns into thorium-234, protactinium-234, uranium-230, thorium-230, and so on and so on and so on down the line. But yeah, eventually we're going to get to lead-206. That's eventually where we end up. It's a little more complicated than just that. Half-life, which is that last part of the column, means how long it takes for half of the radioactive material to decay, hence half-life. How long does it take for half of that radioactive material to decay? And so on the chart, they showed us what the half-life was of those elements. I'd like to give you an example. If you take a look at the boxes over on the right-hand side of your notes, let's use that as an example. Imagine this box here is 400 grams of carbon-14. That's 400 grams of carbon-14. We know that carbon-14 is radioactive. It doesn't want to stay carbon-14. It's going to change into something else. Well, after a certain amount of time, it's going to change half of it. And that amount of time, that half-life, for carbon-14 is 5,700 years. So if you had 400 grams of carbon-14 in a big box, and you waited 5,700 years, eventually you would only have 200 grams of carbon-14. Well, what about the other part? Well, the other part is going to be the nitrogen-14, because that's what it decays into. So that makes sense. After one half-life, half of the carbon-14 is now decayed. Well, what happens next? What about another 5,700 years goes by? Another half-life goes by. It's not all of the carbon is now gone. Only half of the carbon that was there. So we had 200 grams. Now we're going to be down to 100 grams of carbon-14. The rest of the stuff is going to be the nitrogen-14. Notice the amount of material stays the same. We started with 400 grams. After a half-life, we still have 400 grams of material. Here, we still have 400 grams of material. What it is has changed. After one half-life, we have 200 grams of carbon-14. After another half-life, now down to 100 grams of carbon-14. What about another half-life? So another half-life goes by, another 5,700 years. Now I'm only going to have 50 grams of carbon-14. What if another half-life goes by? Another 5,700 years goes by. Now, instead of having 50 grams of carbon-14, now I'm only going to have 25 grams of carbon-14. There's barely any left. And what if another half? Well, we could continue this process again and again and again and again and again. Notice how the amount of carbon-14 cuts in half each half-life, from 400 to 200 to 100 to 50 to 25. The half-life never changes. The half-life of carbon-14 is 5,700 years. Here the half-life is 5,700 years. Here the half-life is 5,700 years. Here the half-life is 5,700 years. Here the and it keeps going. We could, if our paper was long enough, we could just continue this process again and again and again and again and again. The half-life of carbon-14 is always 5,700 years. The others have different half-lives. Notice that potassium-40, its half-life is 1.3 times 10 to the 9th years. Ooh, let's put that down. 1.3 times 10 to the ninth. So let's take that decimal and move it over 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fill that in with some zeros. Let's see what this is. 1.3 times 10 to the ninth. That's a pretty decent number right there. So there's a comma there, there's a comma there, and there's a comma there. So we've got our thousands, millions, billions. 1.3 billion years is the half-life of potassium-40. So 1.3, whenever you see times 10 to the ninth, that means a billion. So 1.3 billion years. Uranium-238, 4.5 billion years. Rubidium-87, 49 billion years. Those are quite different compared to our carbon-14, where we said 5.7 times 10 to the third. 5.7 times 10 to the third, move that decimal over 1, 2, 3, is just 5,700 years. Carbon-14 is a little special. It's the one that stands out because it has a short half-life. Carbon-14 is not only special because of its short half-life, it's also special because it's the only one that's found in organic material. Potassium-40, uranium-238, rubidium-87, those are used generally to find the age of very old rocks. Yet carbon-14, since it's found in organic material, is used to find the age of very young. And when I say very young, we mean talking about less than maybe 70, 80,000 years. Carbon-14 is used to find things that are young and organic, bones, teeth, fossil material. That's where we're going to use carbon-14. So of these four, when you look at this, carbon-14 should stand out to you. What are we going to use this for? Now that we know this, we can figure out the age of certain materials, knowing how much radioactive material there is. For instance, if you look at this, which bread do you think is the oldest? Obviously, C is the oldest. It's got the most amount of decayed material. It's got the least amount of bread left. You can look at this chart similar to that. Here's the material that's radioactive. This is kind of like the bread. And then we also have what it decays into. This is kind of like the mold in this analogy. The more of the original material that we have, the younger the material is. The more decayed material, the older it is. For instance, let's use this. A whalebone that originally contained 200 grams of radioactive carbon-14 now contains 25 grams of carbon-14. So it started with 200 grams. It's now down to 25 grams of carbon-14. How many carbon-14 half-lives have passed since this whale was alive? Well, let's take a look. We're starting with 200 grams of carbon-14. Let's take a look at what that looks like. So I'm going to start with 200 grams of carbon-14. After one half-life, right, a half-life, I'm going to be left now with 100 grams of carbon-14. After another half-life, now I'm down to 50. Now I'm down to 50 grams of carbon-14. And yet another half-life goes by, and now I'm finally down to what the question was asking about, 25 grams of carbon-14. Let's take a look at the question again. The question says, how many carbon-14 half-lives have passed? When we look at this, we see that there have been 1, 2, 3 half-lives. Be very careful. Some people like to count when they draw this. They go, oh, 1, 2, 3, 4. No, it has not been 4, right? It's only been 3 half-lives. We could also then figure out how old that is. Well, if I know that the half-life of carbon-14 is 5,700 years times the 3 half-lives that it's been, I could easily figure out that that would be 17,100 years. That's how old that whalebone is.